teaching in the rain. I'm teaching in the... I actually am teaching... Well, this is Laramie. No doubt when you're watching this in the snow. But I happen to be teaching this in the rain because we have had so much rain lately. And the mosquitoes are loving it. And we are not. Okay, so confidence intervals. Here's our equation. I want you to realize this equation is not something new. Let's start with what we did before. Here's our equation. Z equals x bar minus mu over sigma divided by square root of n. If you're uncomfortable with this equation, that's a bad thing. Come talk to me. All right? This is when we know mu and we're trying to get a z. For confidence intervals, it's the other way around. We know our z. In fact, we have two different z's. So I'm going to give him a plus or minus. Two different z's. What we don't know is the mu, and that's what we want to solve for. So let's solve this equation for mu. What would I do? I'm going to move the sigma over square root of n to the other side, right? You do that by multiplying both sides. So I get a plus or minus z. Sigma over square root of n is now being multiplied, and on this side, it would disappear. Okay, I'm solving for mu, so I'm going to add mu to the other side, and then I'm going to subtract this guy to the opposite end. Now, because he's plus or minus, when I subtract him, he would go minus plus, but that's just confusing. So I'm going to switch plus or minus because the order doesn't matter. The order does matter in the computer. When you get a confidence interval, the smaller number, the number you get from the minus, that's what goes first. The positive number, what you get from the plus, that's what goes after. If you mix those up, it's going to tell you it's wrong. And looky there. There's our equation. Now, to be fair, this z gives you a range from what you get with the minus z to what you get with the positive z. So putting an equals here is technically wrong. Your math teacher would have a fit. There is a special symbol for saying it belongs to this range. It looks kind of like a weird E type thing, but if that's confusing, just don't worry about it, okay? Your math teacher cares. In this class, not so much. Here's the equation for a confidence interval. Now, let's talk about how you can affect that confidence interval. What kind of things can you do to it to make it smaller? Now, smaller means you've zeroed in on where mu is. So having a smaller confidence interval is a good thing. You always want everything to get smaller.
To get a smaller interval, use a smaller confidence level. For a bigger interval,
you would use a bigger confidence level. Let me explain why with a picture. If I do 95% confidence intervals, that means I'm trying to capture 95% of the area under my normal curve. That's going to give me a big interval. But if I lower that level, and now I say I only want 90%, I've zeroed in on that. So this is very confusing for students often because you think confidence is a good thing, but having less confidence shrinks your interval, which is a good thing. It's actually a trade-off. If your confidence level drops, which is bad, right? We are less confident about our answer. The trade-off is your confidence interval shrinks. It zooms in on where that correct answer is. So if you're doing a lower confidence level, then you're more likely that you're going to make a mistake in your calculations. But it's going to look better as far as the confidence interval is concerned. So this is the difficult trade-off between these two. Why don't we use 100% confidence? 100% confidence means you are guaranteed to get the right answer. Look at the picture. If I want 100% confidence, how far out does it have to go? Negative infinity to positive infinity. I am 100% confident that today we will get between negative infinity and positive infinity amount of rain. Yeah, gee, great, thanks a lot. Absolutely worthless. So 100% confidence doesn't work. Now, if I wanted to say I know exactly how much rain I'm going to get, well, I can do that if I go to 0% confidence. But 0% confidence means I'm using a method that has 0% chance of working. And that makes sense, right? You're going to claim you know exactly how much rain you're going to get. There's a 0% chance that you're going to say it exactly down to the nearest 12th decimal place, okay? So there's this trade-off between how much do you do. The most common confidence level, because of this trade-off, is 95%. We use 95% confidence level most of the time because that's just what everybody does. In your homework, you're going to see a lot of numbers, not 95% confidence. Here's one rule. The opposite, of course, is also true. that if you use a higher confidence level, instead of 95%, let's go to 99%, then your interval is going to grow. The reason that makes sense is because if you want to be more confident that you got the answer right, you're going to include more numbers. So that's the trade-off. There's some other things that can affect confidence. For example, if you increase your sample size, your confidence interval shrinks. I hope that makes sense intuitively. If you sample more data, then you can be more accurate. Here is where the mean is. How does that work mathematically? If this gets larger, you're dividing by more. Dividing by more means this part gets smaller. Plus or minus less, you're plus or minusing less, it shrinks in. Okay, so intuitively or mathematically, that should make sense. This is what statisticians often do. If you really want to shrink your interval, instead of playing with your confidence level, go out and collect more data. Bad side is it's expensive. And then there's sigma. If you can shrink your sigma, then you can shrink this number, your interval is smaller. In other words, if you can make it so there's less error in the system, then you're going to be able to zero in on where mu is easier. Unfortunately, that's not very realistic. You can't just shrink things by wishing, I wish it could shrink.
So get lots of data. The opposite here is true. That's all